It's my pleasure to introduce Laure Resplandy today to the STEP David Bradford seminars. The organizers, which are Denise Mazarol and Howard Shapiro and myself, actually have been trying to bring local and young talent and intersperse them with the more established talent we've been having at these talks. And Laure very much fits the profile of a local rising star. She has been at Princeton since this fall of 2017, in both the geosciences and PEI. She got her PhD in oceanography at the Sorbonne in 2010, and then did a 2-year postdoc in the UK, back to Paris for 2 years, and then most recently 2 years at the Scripps Institute with Ralph Keeling's group. And her research is on the connection between ocean circulation, biogeochemical cycles, and the Earth's climate, and she does this both at the global scale and remarkably also sizing down to the local scale between 1 and 10 kilometers. Her research is well funded by NASA. She has actually 3 grants from NASA right now. She already has 28 publications in journals that range from climate dynamics to geophysical research letters and PNAS. And today she's going to tell us about her work on ocean control of climate, challenging heat and carbon budgets.
Thank you very much.
Laure.
Okay, thank you. Do I need to? I don't need to talk in this, no. No. Okay, thank you for inviting me here today. I'm going to talk about some of my global work on climate and global carbon and heat budgets. That's something that I've started at Scripps with Ralph Keeling, but it involves a lot of people. So these are all my collaborators. And I'm continuing to work on this now that I'm at Princeton. Okay, so why the heat and carbon? Well, because they are, yes. Okay, so I have to talk in this so you can hear me? I have to talk like this? That's going to be great. Okay, so why the ocean heat and carbon? Well, because heat and carbon are important for the climate system. And here, so a lot of my plots today are going to be similar to this. So,
sorry.
Okay, is that better? Okay. So this is, see that as it's the whole ocean collapsed into a slice. And it includes all the basins, the Atlantic, the Pacific, the Indian Ocean, the Southern Ocean. It's as if here you have the x-axis is latitude, so you have the South Pole down there, the North Pole up there. And here you have depth. We do a lot of those plots in oceanography, so it's really depth, how it looks like the ocean as a function of latitude. And here I show warming and anthropogenic carbon. Anthropogenic carbon is the amount of carbon that was emitted by humans in the atmosphere, and that has actually been taken up by the ocean since the beginning, since we started to emit carbon. So here you see the warming pattern and the carbon pattern. This is how they enter the ocean. And why are they important? Why is the ocean important for carbon and heat? Well, actually the ocean takes up 90% of the extra heat, of the extra warming on the Earth system. And it takes about 30% of the extra carbon that is emitted to the atmosphere. And so it has, to understand those patterns and how the carbon takes up those perturbation of the system, it has value first because they're going to have an impact. For example, if you think about warming or carbon in the ocean is going to acidify the ocean and they're going to impact the ecosystems, their physiology, but also because the ocean buffers the system. Because it takes up so much of that perturbation, it's going to buffer the temperature and the system, the carbon in the atmosphere. And if you look at that perturbation and you overlay what is the main circulation and transport in the ocean, so you have the surface waters where a lot of that warming and carbon is accumulated because it's in contact with the atmosphere, but then you do have heat and carbon entering the ocean, and that follows those main currents transport by the ocean from intermediate waters, deep water that sink in the north, and bottom waters that sink in the south. And so to understand those perturbations, you need to understand that natural transport of carbon and heat in the ocean. And that's what I'm going to talk about today. And I'm going to look at how well do we know that ocean natural transport of heat and carbon, and what are the implications for the Earth system. And I'm going to start with the ocean heat transport. And what I'm going to do, I'm just giving you a little peek of what I'm going to do. I'm going to use some atmospheric data to constrain the ocean heat, and I'm going to talk about the implication for the climate system. So what does the ocean do in terms of heat? And that's a map of the air-sea heat flux, so the exchange of heat between the atmosphere and the ocean. Red, it means the ocean is gaining heat, and blue or purple is the ocean is losing heat. So basically what is happening is the ocean is absorbing heat in the tropics at the equator, it's transporting it poleward, and then it releases it back to the atmosphere at a higher latitude. Especially here, that's the Gulf Stream, for example, that's the Kuroshio, the western boundary currents here in the North Atlantic and in the Southern Ocean. However, it's not symmetric. The ocean releases more heat in the north than in the south. And so actually there is a total heat transport from the southern hemisphere to the northern hemisphere by the ocean. And to understand why, you can see a very simplified, most of that asymmetry comes from the Atlantic, so I'm going to simplify here. The Atlantic circulation, if you really simplify it, is a loop with the North Pole is here, the South Pole is here, and you have water that deep waters sink in the north, they transport deep waters south, and they come back up, and then surface waters are going northward. And so if we look at, we all know that temperature decreases with depth in the ocean, so it's going to be warm at the surface and cold at depth. So that loop, what it's going to do is that it's going to transport mostly warm waters northward and cooler waters southward. So as a whole, you transport heat northward. So why is that important? Well, it's actually it's a very important feature of our climate system. And I'm going to give a couple of examples. So the first one is tropical rainfall. The fact that the ocean transports heat northward is going to set what we call the thermal equator, meaning where the heat is maximum, is where the heat transport is going to be maximum, the heat gain is not at the equator, but it's actually shifted northward. And if you look, this is a map of the annual precipitation on the globe, the maximum of annual precipitation. And you see that a lot of the precipitation is happening, if you focus just on the tropics, is located north of the equator. And that's because of that northward heat transport. If the ocean was not transporting heat northward, it would be like aligned with the equator. And we call that area the intertropical convergence zone, because it's the zone where winds converge and you have those huge clouds, convective clouds that they look like this. This is a vision from, this is an image from space. And these are those huge clouds that's in India during the monsoon, because that convergence of the wind is going to control the monsoon, is one of the things, and they can control tropical rainfall, but also monsoon. And so the amount of rain that is or there is not is going to be important for population living, very important for population living in that area. So one of the things that I'm going to look at is if you reproduce that heat transport well or not in models, for example, you're going to be able to reproduce better or not the rainfall patterns and their maybe projection also in the future. Another aspect is Arctic sea ice. And here I'm showing two maps. One is an average of it's the sea ice extent, the sea ice concentration, in the Arctic. And you see in red are observations for 1980s to 2008. And you see here the sea ice concentration in colors is an average of models that have a strong northward heat transport. And here you have an average of several models that have a weak northward heat transport. And they see that depending on the magnitude of that heat transport, you have a different sea ice concentration and extent in the Arctic. And you see something to remember for later is that it looks like model with a strong northward heat transport have a better match with the observation. So it's going to be important for the climate, so that heat transport for rainfall, for sea ice, these are two main features. Okay, so what do we know about that heat transport? How big it is? And here I'm showing what I'm going to talk about a lot in that talk is the asymmetry. The asymmetry, what I call the hemispheric asymmetry, is the difference between the northern hemisphere and the southern hemisphere. So I told you that the ocean is gaining heat in the tropics, then it's transported it, and it loses it at higher latitude. And I told you that it loses more in the north than in the south. And you can measure that asymmetry between the north and the south using what I call A, or the asymmetry. It's just the mean of the transport at 20 south and 20 north. And it's going to really give a measure of, at steady state, that might compensate how much more heat you're losing in the north compared to the south. Okay, so how do we know that number? Well, we can estimate that transport by the ocean with ocean sections. So it's really ship going, measuring along like sections in the Atlantic, in the Pacific, in the Indian. It's very hard to do because you need to measure a lot of ocean. But we have some ocean sections. Then you have surface flux chromatology. So if you have those numbers here, those arrows from satellite or atmospheric observations, you can get also that number because they must compensate. Or top of the atmosphere, this is based on satellite that measure the energy imbalance at the top of the atmosphere. And you can also get a sense, this is a very indirect method, but you can get a number. And basically, they are between 0, almost, and 1.1 petawatt. Petawatt is 10 to the 15th watt. Just to give you an idea, that's about the amount of that heat that is transported by the ocean is about 5 times the total warming that we experience every year. So it's a large amount of heat that is transported northward by the ocean. Okay, so basically my message here is we have a large range. It's not very well constrained, from 0 to 1, which would be from 0 to 5 times the global warming signal. So it's very unconstrained. So what I've done is, can we constrain that number better? And what I used is, that's the concept. So can we use inert gases in the atmosphere to measure that heat transport? And that idea comes because the flux of an inert gas F across the interface in the ocean depends on the heat flux. It scales with the heat flux. And you have kind of that, it's not an inert gas, but if you leave your Coke in the sun, it's going to lose that CO2. And it's going to lose the gas. And that's kind of the same idea, is that if your ocean is cooling, it's going to take up more gas, and if it's warm, it's going to lose more gas. And it scales, and it depends on solubility, but we can compute that. So we have a scaling. If we get that inert gas flux, we can get to the heat flux. And so if we have more, how can we measure that in the atmosphere? Well, if you measure, that's kind of 2 boxes in the atmosphere, one in the northern hemisphere and one in the southern hemisphere, and you compute, like you measure the amount of gas. Because you have more going in the ocean in the north, you should have a deficit in that gas compared to the southern hemisphere. An inert gas is not going to change because of biology. It's really inert. That's the only thing that's going to matter. It's thermal exchanges. So if you could potentially track heat fluxes using inert gas concentration in the atmosphere. You can tell me, why would you measure ocean heat transport using the atmosphere and not, why is it simpler than directly using ocean measurements? And that's because the atmosphere is very well mixed within those latitudinal bands, because most winds are going along at one latitude. And so actually with very few measurements, you can have a very good idea of what's going on at the interface. Whereas in the ocean, you need to measure a lot, like thousands and thousands of points to get the same information. So that's why it's interesting to look at the atmosphere to actually infer what's going on in the ocean. Okay, so inert gas, perfect. However, today we don't have inert gas measurements that are precise enough to do that. But we do have a gas, a tracer that behave like an inert gas. And that's called potential oxygen. It's oxygen in the atmosphere, but we combine it with CO2 in the atmosphere. So why is that interesting? Well, O2 and CO2 in the atmosphere, they change because of ocean exchange, but they also change because of fossil fuel burning, terrestrial biosphere, just photosynthesis, respiration. But we know those ratios here on land. And so by combining O2 and CO2 together, we actually remove the influence of terrestrial biosphere. So we remove that. And then we know how much fossil fuel, with quite a good uncertainty, we know how much fossil fuel we emit, so we can actually remove that. And we're left with a tracer of ocean exchange only. And we can define a mirror tracer in the ocean. It's really that we can measure in the ocean also. Basically, for a certain amount in the atmosphere that goes in the ocean, that's going to increase by the same amount. It's really a mirror tracer. Okay. So now I'm telling you that I can use that to track heat. So why does that work? Well, if you look at observation in the ocean of that tracer, here, these are like more than 8,000 points in the ocean. And that's the temperature at the same point. And they scale very well. That tracer and heat are really behaving like an inert gas. So why is that? Well, because actually, most of the biological effects are like compensate when you combine O2 and CO2 together. So any residual, biological residue that you would have, because photosynthesis and respiration in the ocean is like a little bit like on land, they compensate each other, and you really track heat exchanges. Okay, so we have a tracer that behaves like an inert gas and can track heat exchange between atmosphere and ocean. Okay, but now we need to measure it in the atmosphere. And that's what it looks like. So this time it's altitude, pressure, and that's the same, North Pole, South Pole. And my collaborators, they spent 500 hours in that plane measuring, going up and down in the atmosphere, up and down, from the North Pole to the South Pole to measure those things at 4 seasons. A lot of time in an airplane. And that's what they get. That's the picture they get. And you do see how we expected from our hypothesis that there is a deficit in the northern hemisphere compared to the southern hemisphere. So it's kind of work. And that's linked to that heat transport here that is going to be released in the north. Okay, the units of that tracer are per meg. It's a little bit similar to ppm, to parts per million. And we have a deficit in the observation of 10 per meg, about 10 per meg. Okay. So our hypothesis work. However, how can we link that to, how much heat does that mean? How much heat is transported to explain that signature? And so for that, I used a suite of models with different heat transport. And I computed what would be their atmospheric potential oxygen distribution. And then I can compare it to the data. So in that case, see, the deficit is too weak in that case compared to the data. And by doing this, we can maybe infer how much heat you need to transport to the north to explain what we see in the data. Okay. So this is what I'm showing here. This is this deficit, meaning that the average within that box minus the average within the southern box. And it's 13 different models as a function of the heat transport in the ocean. So positive is northward. So here you have all the heat transport that is positive. And here negative is southward. So you have models that actually transport heat southward. But most of them transport heat northward in the ocean. But you see that it goes from, minus 0.2 to 0.5 petawatt. And you see that the amount of heat that they transport really scale with their potential oxygen signature in the atmosphere that we expect. Now, down there is the range of the data with the uncertainty. You see that none of the models are actually able to reproduce that very strong blue-yellow pattern that I was showing. But if we think about, okay, if we believe that trend, that relationship, we can get, okay, we need at least 0.7 to 1.1 petawatt of heat transported northward to be able to explain our observations. Because although none of them reproduce the data, they do align on a pretty good line, with it's very tight correlation. So we have a number, 0.7 to 1.1. How does that compare to the previous observations that I was showing? These are all you remember, ocean sections, so they were covering that wide range here. the flux climatology here, which are the most recent estimates, and then the top of the atmosphere. So we actually overlap with the most direct methods, and we are on the high end of those previous estimates. So that would suggest that we are on the high end of anything that has been published in terms of estimate of heat transport. Okay, so you can wonder why are the models failing at reproducing heat transport? Well, because I was telling you, that's why. What we expect is that you have surface water warm surface waters going northward, cold water going southward. Now, what the models are doing mostly is that they do transport warm water northward. That's fine. However, what's happening is that their circulation is wrong in the deep waters. They are too shallow, and so they transport waters that are too warm because it's not deep enough. It's not cold enough what they transport to the south. And so actually that compensates for that heat transport, and you get heat transport that are weaker to the north. So what are the implications of this? So I told you that most of our climate models do underestimate the heat. We were able to use that along with data to have a constraint on that heat transport. But there are implications, as I told you, for intertropical convergence zone, the precipitation. If you don't have that heat transport right, you're going to have your precipitation band that is going to be shifted towards the equator and not north enough. The Arctic sea ice, so I show those results where you actually have too much ice in those models in the Arctic. And also, I haven't talked too much about this, but this mechanism of heat transport is what's going to regulate glacial interglacial transitions. Because if you weaken your transport, you're going to transport less heat northward, so it's going to accumulate in the Southern Ocean, for example, and so it's going to have an impact on like longer timescale climate. Okay. Now I'm going to link this to the carbon cycle. And how am I going to do this? Well, because heat is transported northward, but at the same time, carbon is transported southward in the ocean. And so I'm going to now look at the carbon in the ocean, and I'm going to start with heat, and I'm going to try to constrain the carbon from that ocean heat constraint that I just showed. So we have a better constraint now on the ocean heat transport. So I'm going to refine the carbon transport and discuss what are the implications for the carbon cycle, including the land carbon sink. So where is the anthropogenic carbon going? So that question has been around for a long time now, but that's kind of, if you look at this graph as a function of time, this is the amount of carbon, and you see here what we emit. So in gray, the fossil fuel emissions. In yellow, the land use change, the deforestation, etc. That emits carbon. And then all that carbon is going somewhere. So part of it, like in gray here, is what we observe in the atmosphere, that stays in the atmosphere. It's about 40%. Then some of it is going in the ocean, and we get that estimate of what goes in the ocean using observations, but also models to fill the gaps, if you want. And then we have everything that we can't account for, neither in the atmosphere nor in the ocean, has to be somewhere else. It has to be on land. So actually what goes on land, the land carbon sink, is estimated by residual of all the other terms, because everything that we emit has to go somewhere. And so that's how we compute in global carbon budgets the land sink. So any issues or uncertainty in the ocean is going to translate into issues or uncertainty on the land sink. So why do we care where it's going? If it's going somewhere in the ocean, on land, why do we care? Well, because if it stays in the atmosphere, you're going to have warming associated to it. If it goes in the ocean, you have things like acidification, for example. Or if it goes on land, you don't have acidification, but you do have a sink that is more vulnerable, that maybe in 30 years is going to burn, drought, or fires, and is going to be released back to the atmosphere. So knowing how the partition between those two is done is important. And so there are two issues that I'm going to look at with this partition today in the global carbon cycling. So again, that's south, north. And what I said that we estimate the land by the residual, it's also true within those latitudinal bands, south, tropics, and northern hemisphere. And that's because, as I said, the winds are mostly along one latitude. And so basically with atmospheric observation, we can constrain very well the sum of the land and the ocean by residual. If you know the ocean, you can deduce the land. However, you have to assume you know the ocean. And so there are two things that are very strange today in our carbon budgets. First, in the southern hemisphere, we have a strong source in most calculations from the land. There is no land in the southern extratropics. It's very unlikely. This source can't be explained by mechanistically. It's very that's an artifact from our methods. So a bias here. In the northern extratropics, what's going on is that we have a very strong land carbon sink in our computations. However, people measuring in the field, they can't give a global number, but they have a good idea of what's going on in plants, in forests, and they say that estimate's probably too large. So these are the two controversies that we can address with our large-scale heat transport and carbon transport constraints. So I was saying we have an uncertainty on the partition between the land and the ocean. So how does that work? Well, if you assume you have a very strong ocean sink here in the south, to explain your sum that you know well, you know the sum. So if you have a very strong, maybe too strong ocean sink here, you're going to compensate with a source because you need to match your sum that you have from the atmospheric data. But if you assume a very weak ocean sink, then you're going to need actually a land sink to match what you see in the observations. So that's to show you that land that we compute is really depends on the assumption that we make on the ocean. It would be the same for the north. So how well do we know that ocean sink, that ocean carbon sink? Oh, sorry. So how can we constrain that first? Well, the main difference between those two pictures, I mean, one of the things that we can use is that actually to maintain that, here you have the same flux going in and the same flux going in the north and the south. So you need very little transport by the ocean to maintain that. Here you have almost like no flux in. So you're going to have a steady state to maintain the system. You're going to transport carbon southward. So basically you can distinguish between those two cases from an ocean perspective by the amount of carbon that is transported in the ocean. So how much carbon is transported in the ocean? How well do we know that sink? We have the sink, so it's maybe a busy slide, but we know the ocean sink by two methods. First, we use what we call ocean inversions. They are basically you have points of data in the ocean, carbon data. You assume you know the ocean circulation using a model, and you infer the flux that you need to explain that. You say, okay, how much of a flux do I need to explain what I see in the ocean? The second method is based on partial pressure of CO2. You measure the partial pressure in the ocean, in the atmosphere right on top. You know the winds. You say, okay, at equilibrium, here's the flux I need to explain those, like on both sides of the interface. Those two methods at the global scale, they agree, but they have very large uncertainty. They agree within their large uncertainty, but I'm going to show you that they have systematic differences. So although they agree with very large uncertainty, they have differences. And one of them is the carbon transport. The first method here, transport 0.2 petagram of carbon is 10 to the 15th gram of carbon per year. So 0.2, and the other methods are almost half. So there is more than a factor 2 between those two methods. These are how we estimate our carbon sink, how much of carbon is going in the ocean. So we have a systematic difference. Can we discriminate between those two? Do we have constraint to say this one is better than the other? And that's what I've been working on with heat. That controversy has been going on for a long time. It started in '89, and I arrived in this. I didn't know that I would be caught up in that controversies with a lot of history in it. So basically, from atmospheric CO2 data, people said 1 petagram must go southward. From models and inversions, people said it's only a third of a petagram. And today what I'm going to do is actually now we have a much longer record on the atmospheric data. We have more recent models. And I'm going to add a heat constraint. And I'm going to show you that we can actually converge to a number that is, I hope, the right number. OK, so why can we understand carbon using heat? Well, in the ocean, if you look temperature, you have warm water at the surface, cool water at the depth. Carbon is the opposite. You have a lot of carbon at the bottom and no carbon at the surface. So basically, that loop that I was describing is transporting heat northward, but it's transporting carbon southward. So that's why there is a link between the two. It's not perfect because carbon is also influenced by the biological pump. And so you have some decoupling between the two, but I'm going to show you that that coupling is strong enough that we can have a constraint on it. And here I'm showing how much carbon is transported as a function of heat. So it's really that carbon transport as a function of heat transport in the ocean. And here I'm using 11 models. We don't have data. We have data for heat a little bit. We have constraint, but carbon, we don't have data except in the Atlantic. I'm not going to show them here, but we don't have data to do that, direct data. And what you see is that here are the cluster of models that transport heat northward, what we expect, positive. And you see that they transport carbon southward. It's negative. And that spread is because of the biological pump. We explained most of that spread between the, like around that line by the biology. We can explain 85% of the variance just with heat and biological pump. What we can get out of this is we know the heat transport from what I showed just earlier. We know how much heat is transported. So we can get a constraint on the carbon. And we get that we need about between 0.35 and 0.65 petagram of carbon that must be transported southward to match that heat observations. Another thing that we see is that all the models fall short. They're all biased low. But that's not very surprising. I told you they were biased low for heat, so obviously they're going to be biased low for carbon. So that's one of the links also. It's if you start to have some biases in the main circulation, in the physical circulation, you have implication for the biogeochemistry and the carbon cycling. OK, but we do have a constraint. If we use that relationship between carbon and heat, it's that number, between 0.35 and 0.65 petagram of carbon. How does that fit in that picture that I showed you? Well, it's in the middle, which is good. It's always better. It's easier for people to solve when you have a disagreement. But we can also update those methods that were calculated before. And actually now, if you use the full time series, the 55 years of data, you actually find half a petagram from that method. You find between 0 and 0.5, some models don't transport carbon, they don't transport heat, but some of them do better than they used to in the past. So I think it's with different constraints, we start to converge to that number that the ocean transport between a third and 0.6 petagram of carbon per year southward. OK, so what are the implications of this? Well, if you go back, you remember I told you we use two types of estimates of the carbon sink in the ocean. The first one is not compatible with that constraint at all. The other one is in the constraint, it's compatible. So depending which one you use to do your global carbon budgets, it's going to have an implication. And I'm going to show you it's going to have an implication on the land sink that you compute. And this is the results. This is the results of how we compute the land sink. And basically, I computed the land sink with using the first method, ocean inversion, and using the second one, where I'm not going to talk about this, but we revised the rivers contribution, which is a big part of the story, but I'm not talking about this today. And basically, what we see in the first case is that we have that source of carbon that I was talking at the beginning. That can't exist. It's spurious. It's not likely. And a very strong sink in the north. If we now compute the land sink with that other revised carbon sink in the ocean that is compatible with the heat constraints that we have, you get rid of that source and you decrease a little bit the northern land sink. And actually, it doesn't seem much, but it redistributes 40% of the land sink between latitudinal bands. Why does it matter? Well, because if it's going in the ocean in the southern hemisphere, or if it's going in a tropical forest, that matters. It will also reduce the gap between those methods that are global methods and what people do, like on the field, measuring ecosystems, forest patches, and measuring, and it really make more sense. It reconciles the both methods. Okay, and I'm gonna just finish on this. So I hope I convinced you that we have some new constraints on the heat and carbon budget in the ocean. I haven't talked about this, but the rivers are largely overlooked in those budgets, but they are important, actually. Another thing that I showed is that our climate models systematically underestimate heat and carbon transport. And that's because although they do have the right amount of water that circulate, it's not with the right properties. It's too shallow. The deep waters formed in the North Atlantic are too shallow. The implications, well, there are a lot of implications with this. So it impacts tropical precipitation, the monsoon system, the convergence zone, in intertropical convergence zone, our prediction of Arctic sea ice, temperature, obviously. In terms of carbon, it impacts the partition between the ocean and land. It has an impact because if the carbon is going in the ocean and not on land, or vice versa, it's going to change your acidification patterns. It's going to also change your prediction of the sink vulnerability. If it goes in the ocean, it stays for 1,000 years. If it's on land, how long does it stay? We don't really know. And yeah, that's it. Yep.
You've slayed a couple of dragons here. One of them is that the ocean transport of heat at depth is different from what everybody has believed. And the other is that the ocean carbon inversions, inferred carbon ocean transport from inversions, are wrong. Those are two big communities.
I know.
So, and it's great. I love it. I love the spirit of it all. Are they pushing back? Are they going
Yes.
back to their measurements? What's going on?
Yes, so I have a lot of pushback, actually, not only from the ocean inversion community, but also the PCO2 measurement community, because they hide the river issue under the carpet. So it's for another reason. They hide the river issue. You know, I said that they hide, like they... So basically, these methods, I don't think they are doomed. So the ocean inversion, I don't think they are doomed. I just think they were using models. They are using the same models that I talked about that are biased. And those methods, they rely on those models. So obviously, they're going to be biased low because they are biased low in their transport. They don't transport the right water masses. So it's not that conceptually that method is wrong. It's just because the tools are not there yet to use it in that sense.
It must be in part because we aren't measuring the deep ocean flow well enough.
Yeah,
Right?
so our models are not very well constrained, and so that method cannot rely on measurements, direct measurements. It relies on models. And because our models are biased, obviously the estimate that you get out of it is biased the same way. The second method, I think is working really well. However, it's PCO2 data, partial pressure of CO2 plus rivers. And that's the thing, is rivers used to be a small term compared to uncertainty for a long time, but now that we have reduced our uncertainty everywhere else, rivers become an important factor. They are more than half a petagram of carbon. And so that's the main, I think that's one of the main challenges today.
So you basically mentioned about that the carbon is going northward?
Yes, no, southward.
Southward.
Yep.
And is it possible to like build like an artificial cell, like proto cell, to eat the CO2 under the water?
So an artificial what?
Like proto cell, like artificial cell.
A cell of what?
Like, is it possible to design a cell that eats carbon dioxide? Or like, you just basically use two methods. Is it possible to have a third solution for that?
You mean to measure carbon?
No. I mean, to eat the CO2.
To eat the CO2?
Yeah.
Okay. So what I'm showing here is not, it's just the occurring natural cycle. It's really transport of carbon. It's not that it's eaten away. It's really carbon flows in the ocean when you have currents, and they transport stuff. They transport heat because they have different temperature. They transport carbon. They transport particles. They transport plastic. They transport anything. They transport a lot of things. And they do transport carbon. So what I'm talking about is really the transport of carbon. However, what I guess you're referring to is, can we like increase that sink of carbon in the ocean? Like, can the ocean take up more than 30% maybe?
I think what he's asking about basically also exactly what you're saying is probably outside of the scope of what you're describing here, but he is looking for a solution where will you be able in the future to manipulate gases in the atmosphere or in the ocean where you're able to get somewhat close to the optimal level of what you need.
So there are a few.
We're all looking for.
There are a few avenues that are looking at, and for the ocean part, a lot of it is you increase the biological production, and so you would capture more CO2.
How do you do that?
So biological production in the ocean, photosynthesis is mostly limited. So one of the limiting factors is nutrients. And so one of the proposed things is to add iron, because one of the limitations, for example, in the Southern Ocean is iron. So if you add iron, you would increase the amount of carbon that is captured by photosynthesis. However, you would change completely the ecosystems. You would, and for all the carbon that you capture only at the surface, only about 1% is actually stored on long time scales. So personally, I don't think that method is worth the perturbation that it's going to do. In the end, the carbon that is in the atmosphere is going to go in the ocean, because that land-ocean partition that we're talking about is on our time scales. In 1,000 years, it will be, or 2,000 years, it will be in the ocean, just because the ocean is the big buffer of the carbon system, and in 1,000,000 years, it will be in rocks. So in the end, it's going to go in the ocean. But I'm not really convinced that those methods on photosynthesis in the ocean are a good idea. I'm sorry. Yeah.
I think you might have mentioned it and I've forgotten already or missed it, but what's the overall implication for the sinks going forward? Is it that there's a bigger ocean sink and it's more confident that it'll keep going, or is it?
Yeah. So the implication is that if you attribute to the wrong sink, so basically what's happening in that last picture is that people are saying a lot of that carbon is going in the Southern Ocean, but actually it's not going in the Southern Ocean. So it will change, and it might be more, you see here, I haven't talked about the tropics, but it might go more in the tropics. And so it completely changes your prediction and your projections, because if you think your carbon is going in your Southern Ocean, but actually it's going in your tropical forests, if you have that wrong in your models to start with, your projection is going to be completely different, given those assumptions. So it's at the moment, it's not necessarily saying that you have more carbon going in the ocean or less. It's more that knowing where it goes between the redistribution between those land and ocean is what is going to make processes are different. If it goes in the Southern Ocean, it stays there for hundreds of years. If it goes in the tropical forest that we are cutting down, it's just going to go back in the atmosphere in 20 years.
The overall balance isn't that much different here. It's
Yes, that's what I'm saying. The overall balance is driven by atmospheric observation. If you know your fossil fuel emission, you assume land use, but fossil fuel emission, and you know what's in the atmosphere, then you know that amount that you're missing went either in the ocean or the land. That you know. So actually on that, we have pretty good constraints because we know pretty well fossil fuel emissions, 10% uncertainty at max. And we know the atmospheric observation, we have a good network. We know how much is in the atmosphere. So actually the sum of ocean and land is very well known. But then knowing where it goes exactly and that's where the problem is, and that's important because in your model, mechanistically, if you're putting in the ocean instead of the tropical forest, it's completely different and it will evolve differently. And it will have different impacts on acidification, warming. Yep.
Do you need to specify the latitudes over which meridional transport takes place, and does that introduce any uncertainties in the calculations?
Yes. So that's why I took those big regions. In theory, you could say you could do it like very small slice. Look at the south, like here, that slice. But that's where then our uncertainty in the atmospheric transport kicks in. So we have relatively good constraint on extratropics versus tropics because you have a natural boundary at the equator between those two main regions. You need 1 year to mix your atmosphere between the northern hemisphere and the southern hemisphere. You need about 1 year. So you have actually a clear separation between north and south. I haven't taken just the equator because I don't want to be dealing with that moving intertropical convergence zone that is going to change the thermal equator is moving around during the year. So basically what I'm doing here, I'm removing all the tropical, the uncertainty in the equatorial circulation because that's where my uncertainty comes. So now what you're saying is that I used here one atmospheric transport to compute that. If I use another atmospheric transport, I will get slightly different numbers. However, the systematic difference between those two cases will still be true because within that known, that you assume you know atmospheric transport, the systematic bias between north and south is the same. But we do have uncertainty in the exact numbers here. Obviously, we do have uncertainty on that.
So the model you use makes the biggest difference in the south. Is that right?
So
Yours versus
this.
previous models?
So I don't use a model in that case. I use a series of models to establish a constraint, but actually this is based on observations, that constraint that I get. Yes, so that observational based constraint gives me less of a sink in the Southern Ocean. And I should say that we have a big program at Princeton that is called SOCOM that measured the carbon with floats in the Southern Ocean. And what they found is for the past couple of years, they measured carbon, because that's the problem in the Southern Ocean. We don't have measurements. And they provided with that program a very, the first winter data that we have in the Southern Ocean. And they find something that is compatible with that view, that actually the Southern Ocean is less of a sink than we thought it was. So from atmospheric constraints, from ocean float constraint direct measurements, we seem to converge to that result.
Any more questions for that? Thank
Can
you,
you just
Laure.
remind me what the units of measurement are here?
So that's petagram of carbon. Yeah. Yeah.
So small differences are huge, yes.
Yes, that's 10 to the 15th gram of carbon per year.
Ten is the emissions.
Thank you very much.
Thanks.